So, the next problem that we look into based on dynamic programming is all pair shortest paths, and this is Floyd-Warshall's algorithm. Earlier occasion I have presented to you in earlier videos in greedy method algorithm for single source shortest path, and that was Dijkstra's algorithm. So, at that time I made a mention about this problem as well, which is called all pair shortest paths, meaning finding shortest path not from one vertex, but from all vertices to every other vertex, all pairs. That means, for all pair of values of I and j, we would like to find the shortest path rather than single pair or rather than from one source to other vertices. You get my point? All pairs. This is one problem which can be solved using both greedy and dynamic programming. How can we solve using greedy problem? You can use Dijkstra's algorithm of single source shortest path and run that algorithm n times, every time changing the source vertex. First time you apply Dijkstra's single source shortest path from vertex 1, then you apply from vertex 2, then you apply from vertex 3, I will get the solution for all pair shortest path. But since principle of optimality applies, the optimality substructure property holds. So, therefore, like other problems of dynamic programming, for this problem also we can derive a dynamic programming based recurrence as a solution to the problem and then get a solve the problem. Okay. So, let us see the development of the solution recurrence for this problem. So, like previous problems, here also this is the simple graph I have taken, graph with only 3 vertices 1, 2, 3, and the graph is represented through adjacency matrix, where I say Cij is cost of the edge. Again I have written cost of the edge between vertices I and j. Okay. Like cost of the edge from 1 to 2 is 4, 1 to 3 is 11, 2 to 1 is 6, and 2 to 1, and then 3 to 1, there is no edge from 3 to 2. So, therefore, infinity and so on. Got it? Okay. Now, the question is, I want to find the shortest path from 1 to 2, 1 to 3, 2 to 1, 2 to 3, 3 to 1, 3 to 2, okay, all pair shortest path. So, that can be very well developed by deriving another matrix A which holds this definition. Let A power k I j represent cost of the tour, cost of the path, or cost of the, not tour, here tour is for traveling salesperson problem. So, cost of the path between vertices I and j, that means source and destination, with highest intermediate vertex being k. See, in a path between two vertices I can have several intermediate vertices, and moreover here my convention is I am having the numbering of the vertices in the order from 1 to n, means all vertices of the graph are sequentially numbered from 1 to n, like 1 to 3. So, point is, between any two pair of vertices I can have several intermediate vertices. Just to highlight upon that point, I have taken some sample graph. Consider this graph. Now, if I take my source as 4 and destination as d, as you see in this graph, there are multiple paths between 4 and d. Like some of the paths I put 4, 5, 3, 8, this is one path. Still I can have another path, like for example 4, 2, 6, 7, 8. So, these are called intermediate vertices. Got my point? Intermediate vertices. I can even have a path 4, 5, 10 and 8, these are intermediate vertices, like 4, 1, 9, 8, these are intermediate vertices. I can even take more 4, 1, 6, 9, 7, 8, this is also a path with these intermediate vertices. Got the point? What is the meaning of intermediate vertices? So, now the question is, in this path the highest intermediate vertex is 5, and in this path it is 7, in this path it is 10, in this path it is 9, here also it is 9. So, now the question is, listen to this question carefully, if I am having a graph with n vertices 1 to n, and if I take any two vertices I and j, then what is the highest intermediate vertex x that could lie between I and j is the question. Again I repeat, if I have vertices sequentially numbered from 1 to 10, and if I take two vertices I and j as like for example 4 and 8, what is the highest intermediate vertex that could lie between 4 and 8? Of course, it is 10, is it not? It can be 10, it can be 10 like this, and there can be multiple paths like that, it can be 10. But the question is, should the shortest path should compulsory go through 10? No, it may go through or it may not. Like this may be the shortest path, or this may be the shortest path, or this may be the shortest path, like that. So, what I am trying to say, if I am having n vertices in the graph and if I take two vertices I and j, then what is the highest intermediate vertex x that could lie between I and j? Now, when it is 1 to 10, this is 1 and n, when you are taking I as 4 and j as 8, the highest intermediate vertex that is lying is 10, that could lie is 10. So, in general, for graph with n vertices, the highest intermediate vertex that could lie is n. Then shortest path may go through n, may not go through n. If it goes through n, then I can break up my path as I to n and then n to j, is it not? And if it does not go through n, please follow carefully, if it does not go through n, then the next highest intermediate vertex that could lie between I and j is n minus 1. So, this becomes the basis of my derivation of recurrence. So, shortest path may go through n or may not go through n. If it does not go through n, then it can go through next highest intermediate vertex, namely n minus 1. Again, it may go through n minus 1 or may not. If it does not go through, shortest path does not go through n minus 1, then perhaps it may go through n minus 2. So, now as per the formula, if I write it here, source is I, destination is j. As per the formula, it say the highest intermediate vertex that could lie between I and j is k. So, this is being represented as a k of function a k of I j. So, following my previous argument, I would say that the shortest path may go through k or may not go through k. So, if it goes through k, then I can break up my path into two subpaths. One is from I to k and the other will be from k to j if it goes through. Two paths, optimality substructure property, can go through k or may not go through k. Suppose if I am breaking the path into this, then how do I express the cost of this path? Very simple, the cost of this subpath from I to k, I can write it like I to k, a of I k, and what will be the highest intermediate vertex that could lie here, k minus 1. So, I will write k minus 1 plus what is the cost of this subpath, source is k, destination is j, highest intermediate vertex is k minus 1. So, the shortest path, if it goes through k, this will be the cost, or if it does not go through k, then the next highest intermediate vertex that could lie between I and j is k minus 1. So, if it does not go through k, then I can write a power k I j, I mean I can write it something like this, I j, now the next highest intermediate vertex will be k minus 1, and I can write this as nothing but a k minus 1 of I j. So, whichever is minimum, and I try to work out for all possibilities of intermediate vertices starting with n, n minus 1, n minus 2 and so on. So, based on this I can make a simple derivation for a k of I j as minimum of two possibilities. What two possibilities? Going through k as highest intermediate vertex or not going through k. So, if it goes through k, this is the cost, a of k minus 1 of I k plus a of k minus 1 of k j, or if it does not go through k, a k minus 1 of I j. This I will have to work out for all intermediate vertices starting from 1 to n, because I can have n vertices. So, any vertex can be intermediate vertex starting from 1 going up to n. So, rather it will work starting from n, then highest intermediate is n. So, if it goes through n, well, if it does not go through, then n minus 1, then n minus 2, like that I try until I come to a 1. So, when it become a 1, this will become a 0, please remember this k minus 1. So, this becomes 0, this becomes 0. So, a 0 become my initiating condition of the recurrence. A 0 means no intermediate vertex between I and j. If there is no intermediate vertex between I and j, then obviously and naturally I and j should have a direct edge, and edge cost is given by the function c of I j, is it not? So, c of I j. So, this become my solution to the problem derived based on dynamic programming recurrence. So, again I say this will be the cost of the path if it goes through, shortest path goes through k. If it does not go through k, then k minus 1, then k minus 1 will be computed again in terms of k minus 2 and like again k minus 3 and so on. Got it? So, this is the derivation of the recurrence, and now using this recurrence I will show it to you how to get the solution to the given problem. Okay. Let us see the solution to the problem based on the dynamic programming recurrence that we have derived. Okay. So, for this matrix we are having the value of n equal to 3, mean the highest intermediate vertex k can be 3, meaning we want to find the matrix A power 3, and as per the equation A power 3 will be computed in terms of the matrix A power 2 k minus 1, and then this will be computed in terms of matrix A power 1. A power 1 will be computed in terms of the matrix A power 0. So, that means using the philosophy of bottom up approach, I should first compute the matrix power 0. So, here I will derive the matrix A power 0 of I j. So, 1, 2, 3, 1, 2, 3, this is I, this is j, is it not? A power 0 of I j. So, this is nothing but cost adjacency matrix. So, I am going to copy this entire cost adjacency matrix for A 0. So, let me copy. So, 0 4 11, 6 0 2, 3 infinity 0. So, once I get A 0 matrix, now I can prepare to get A 1 matrix. What does A 1 matrix say? The highest intermediate vertex is 1. Between any two pair of vertices I and j, the highest intermediate vertex is 1. So, here highest intermediate, this is my highest intermediate vertex. So, for your convenience again I am writing highest intermediate vertex between I and j, between I and j. So, let us start working. 1 to 1 there is no meaning in finding the shortest path, I put 0, 1 to 2. Please observe 1 to 2 the direct edge is 4. Now, it say 1 to 2, first I will show it to you by means of formula. So, A of 1 1 2, if I go by formula, what does that mean? Minimum of, come on, A power k minus 1 0, k is 1 0, I comma k 1 comma 1 plus A power k minus 1 0, I k comma j, k is 1, j is 2, correct, or A power 0 k minus 1 I j 1 2. What is this value? This is 0. What is A 0 1 2? A 0 1 2 is 4. A 0 1 2 is 4, minimum of 4 4 4, meaning between 1 and 2 there cannot be any intermediate vertex of index greater than 1, means whatever was the previous value it should retain. So, that is why 4 has come. Likewise, 1 to 3 the known best path so far is 11, that was a direct edge. Now, what does this entry say? 1 to 3 with highest intermediate vertex between 1 and 3 not more than 1. So, this that means again it can be either a direct edge or going through 1 to 3. So, no change. So, this will also be 11. Again if you simplify with the same approach you will get 11. Got my point? Yes. Okay. 2 to 1 via 1, between 2 and 1 I cannot have more than 1. So, naturally whatever is the previous value should be retained again, 2 to 2 anyway 0, but now look at this, look at this. Earlier we say direct edge between 2 3 is having a cost value 2, 2 3 direct edge is 2 3, direct edge is 2, cost is 2, but now this entry say from 2 you can go to 3 via 1, via 1. So, 2 1 3 I can go. So, I should find that cost of the path, or rather you can expand it by equation A 1 2 3 by expansion. This is nothing but minimum of A 0 of I comma k 2 comma 1 plus A 0 direct edge from 1 to 3 k comma j, or A 0 of 2 3. Look at this, A 0 to 1 is how much? 6, A 0 of 1 3 is how much? 1 3 11. What is A 0 of 2 3? A 0 of 2 3 is 2. So, what is minimum? Minimum is 2 itself. That means, if I go from 2 to 3 via 1, look at the graph, 2 to 3, 2 to 3 via 1, 2 to 1 and then 1 to 3. 2 to 1 what is the cost of the edge? 2 to 1 is 6, and then 1 to 3 what is the cost of edge? 11. So, 6 plus 11 17. So, 17 is not better than 2. So, therefore, I will retain the value 2. Do you get my point? Suppose if this value would have been less than 2, then I would have updated here, as I am going to show now for next entry. Now, 3 to 1 direct edge cost is 3. Now, 3 to 1 via 1 no possibility of change. Now, look at this entry, 3 to 2 there is no edge, there is no edge, that is why infinity. Now, with this entry it say that from 3 you can reach 2 via 1. So, then I will have to see can I have a better path. So, again I expand A 0 A 1 of 3 2. So, minimum of what will I write? A0 of I comma k 3 comma 1 and A0 of 1 comma 2 going via 1 3 1 2 or A0 of 3 2. See what happens. What is A0 of 3 1? Look at that. A0 of 3 1 is 3. What is A0 of 1 2? A0 of 1 2 is 4 and this is infinity. So, 7 is better than infinity or not? Look at that. A 3 2 via 1. So, 3 to 1, 3 to 1 is how much? 3 and 1 to 2 is how much? 4. 3 plus 4, 7 is better than infinity. So, change, this is the first change that is happening, this is anyway 0. Got my point? Yes. So, this is the approach of working out the recurrence. Now, once I get the matrix A1, now we can prepare to get the matrix A2. So, again I will put 1 2 3 1 2 3 okay 1 2 3. So, let us proceed to work out in the same dimension. What is going to happen? 1 to 1 0. Now, what is this? Highest intermediate vertex between 1 and 2, between I and j can be 2. Now, between 1 and 2 with highest intermediate vertex being 2, that means I can't have more than 2. So, it should retain the previous value is 4. 1 to 3 now via 2, there is a possibility that you can go from 1 to 3 via 2. So, you have to see from the graph, or I will work out again here for your convenience. A2 1 3. So, what is going to happen? Minimum of A1 ik 1 comma 2 plus A of 1 2 comma 3 or A1 of 1 3. Now, A1 1 2 is how much? A1 1 2 is 4 and A1 2 3 is how much? A1 2 3 is 2 and A1 1 3 is how much? A1 1 3 is 11. So, 4 plus 2 6 and this is 11. So, minimum is what? 6, 6 is better than 11, I update. So, this is the change that is going to happen. You can even look from the graph 1 to 2 and then 2 to 3. 1 to 2 is having cost value 4 and 2 to 3 is having cost value 2. So, 4 plus 2 becomes 6, 6 is better than 11. This is the change that is going to happen. Now, when you come to this entry 2 to 1 via 2, no possibility of change, because between 2 and 1 I cannot have more than 2. 2 to 2 anyway 0. Now, 2 to 3 via 2, no possibility of change. Now, 3 to 1, look at that. 3 to 1, the previous discovered value is 3. Now, from 3 to 1 you can go via 2. So, again if I expand, for example, first entry I will rub off so that I can write it here, you can check. So, if I expand for you, you can check it out. This is important for expansion. A of 2, I am expanding for 3 1. So, minimum of, look at this, A of 1, now I comma k 3 comma 2 plus A of 1 k comma j, k is 2 comma 1 or A of 1 3 comma 1, is it not? Take the values A1 3 2, 3 2 is how much? 7. A1 3 2, look at this, A1 3 2 7, then A1 2 1, A1 2 1, so 2 1 6, is it not? 7 plus 6. And what is A1 3 1? A1 3 1 is 3. So, 7 plus 6 is not better than, that means if I go through intermediate vertex 2, if I go from 3 to 1 via 2, the incurring cost will be 13, 7 plus 6 and the earlier value is 3. So, which is better? 3 is better, no change. This is no change 7, because 3 to 2 with highest intermediate vertex 2 cannot have, and this will be 0. Got my point? So, so far up to a power 2, these are the changes which have been made. You have to work out in a similar way for getting the matrix A3. So, let us work out quickly. Matrix A3, that is the final matrix 1 2 3. Look at that, working in the same way, 1 to 1 no change, 1 to 2 via 3. So, this I can have a possibility. So, I can, because the graph is simple with 3 vertices here. So, how do we work out? 1 to 3, 3 to 2. So, let us see what is the cost from 1 to 3. 1 to 3 is 11, 1 to 3 is 11 and 3 to 2 is 7. So, 11 plus 7 is 18, okay. And then earlier value was 4. So, 4 and 18, 4 itself is better, no change. got my point? And 1, 2, 3 via 3 no possibility of change. So, this will remain 6. Wherever there is a confusion, you can simply use the formula and put it, because I can do it orally, I am putting the values. Otherwise, for you, whenever there is a confusion, simply use the formulas like this and try to evaluate. Okay. Now, 2 to 1 via 3, from 2 to 1, not going through 3 was having cost value 6, but now going via 3, can I have a better path? 2 to 1 via 3. So, 2 to 3 first, 2 to 3, 2, and then 3 to 1, because I want to go to 1, it is like this, 2, 3, 1. So, 2 to 3 previous value k minus 1, 2 to 3 is 2, and then 3 to 1 is 3. So, 2 plus 3 how much? 5. 5 is better than 6, current value is 6. So, 5 is better than, so update 5, this is anyway 0. Now, 2 to 3 via 3 no possibility of change, and then 3 to 1 via 3 no possibility of change, 3 to 2 via 3 no possibility of change. So, this is as usual this. So, what I am trying to say, the final matrix with highest intermediate vertex between I and j, any I and j, is this. So, from the initial matrix, this was my initial matrix, the changes that has happened you can see is for these which I have rounded. So, these are the changes that has taken place as a result of working out this problem. Okay. So, this is the approach of Floyd-Warshall's algorithm for discovering the shortest paths. So, if at all there is any path between vertices I and j, if there is any path between vertices I and j, that can always be discovered with this Floyd-Warshall's algorithm. So, whether the graph is directed or non directed, generally it is a directed graph, even if it is undirected will work out. So, if there is any if there is any path between vertices I and j, then that path will always be discovered, and if there are multiple paths, then shortest path will always be discovered. So, this is the basic philosophy of solving this problem based on Floyd-Warshall's algorithm. Okay.